Okay. Yes. Oh, it might. Okay. So where we were just at the fun part, which is in subsystems. We have the Swerve subsystem here. Okay.
Yep.
Great.
Mm-hmm.
So now let's get started. Can you see it, or do you want me to make it like like bigger?
I can see it fine, and if I need it bigger, I can actually zoom in. So.
Okay, sure. So here, this Swerve drive base, it extends subsystem base. So all subsystems will extend this subsystem base. Again, the kind of the global variables that are relevant, or the variables that are relevant to this Swerve drive, um, this Swerve drive subsystem, is what's called odometry. This is basically responsible for tracking yourself on the field. So
Okay.
tracking where you are on the field. So again, you're going to be using the gyro to update your odometry. You're also going to be using your encoders to track how far your wheels have traveled. And that basically will tell your robot where you are on the field. Okay.
Mm-hmm. Cool.
The next thing is swerve modules. So again, as we actually deployed to the robot, where you can kind of like group motors together into a module.
Mm-hmm.
So the idea, right, is that if you need to, okay, so we'll get into that in a second. So this is all of your modules, and here's your gyro. So these are the three variables that your swerve drive is going to need. That's pretty good. That's like three of them. So here, this is the constructor. Here, what we're doing is we're initializing the gyro, okay, as a pigeon 2. And this right here is the ID that you can get from Falcon Tuner, like which, what number port it's on or whatever. This, I guess, configures it, and then we call the zero gyro method, which kind of like says, okay, now right when this is created, zero the gyro. Okay. The next thing we do in the constructor is we set up our swerve modules. Again, the swerve, so each swerve module refers to like back left, back right, front right. And you'll see
Mm-hmm.
here that we have an array, an array of swerve modules, and there's 4 of them, right? So 0, 1, 2, 3. You'll see here that this pulls from constants. So if you go over here to constants, you'll see that the constants are the drive motor. So this is the motor here. So the ID of the motor. This is the ID of the angle motor, so the turning motor. This is the ID of the CAN coder. So this is like the encoder. I mean, sorry, the encoder. And this is the angle offset. This is very important. This angle offset, basically, if I go to Excalidraw, let's say you have your wheel module like this, okay?
Mm-hmm.
And maybe we went through this example, maybe not.
I
But
don't think so.
okay, so let's say your you have to base it. So you have an encoder, the CAN coder, right? When you read
Mm-hmm.
the CAN coder value, you basically, it's going to be some like random value. Let's say 300, okay? But what we have to do is we have to basically like tell it which way is forward, right? So basically what this offset means is we have to like physically like to tune the robot or to like set it up. One of the steps you're going to have to take, so you're going to take these modules, you're going to physically face them kind of all front to back, okay? And you have to make sure they're lined up. And then what you do is
Yeah.
you find what value on the CAN coder is being read. So let's say forward is 300. So that means now if it's at, if I now read a value of 360, I have a reference to go based off of. Because, does that make sense? It's kind of like if you have this
Oh,
360 value, it's like, well, what does that mean? What is it relative to? So what you have to do is you have to kind of give it kind of a baseline. So what it'll do in order to get the accurate angle of the module, it takes 360 and subtracts it from 300. So it says this angle is 60 units, whatever that means. And then there is a conversion factor between this value of 60 and like how many ticks is a full revolution. Does that make sense?
kinda. So wait. So this can coder value is something that is being read by the can coder, right? This isn't something that we input.
This can coder value is something that is going to be read by the program. And
Okay, but
let's say it's a
we
value
have
of
to.
100. Okay?
Uh huh.
What does 100 mean? Does that mean it's forward or backwards, or does that mean it's at a 45-degree angle, or what? So what we have to do is we have to say, let's say 100 means it's forward. It's like completely straight. So then if later we read, 200, and let's say a full revolution is, full rotation is 400. So let's say offset, let's say the offset is 100. So that's forward to backwards is 100. And then later we read a value of 200. And this is a hard-coded setting that which we have, which is 400 means a full rotation. That means that when I read 200, what that means is I take this 200, subtract it from the offset, which means that we're 100 ticks away from vertical, from front back. So that means that we would be at 90 degrees, right? Because 100 is a quarter of 400. So that means if you take the circle and you divide 360 by 4, you get 90. If you did not have this value, you'd be like, well, what does 200 mean? It needs to be with respect to something that I tell this is something I know. Does that make sense?
Yeah, I think so.
So what you have to do is this value you can get from Phoenix Tuner, where basically you go to the CAN coder and you go to the graph or the visualizer and you rotate the module and you'll see that number change, the reading change. So what you do is you basically you point the wheels forward, and then it says, oh, okay, the CAN coder says that this number is, this baseline is 100, so you just put 100 in here. And then from there, the program will know, oh, I need to go 45 degrees, it's this amount of ticks. Does that make sense?
I think so. So let me just understand that.
Mm-hmm.
So we need to find the value the can coder reads when they're physically aligned the way we want, and then we need to input that value into the angle offset variable.
Exactly.
Cool.
Perfect. And so now we take all of these parameters and we kind of bundle it up in what they call a swerve module constant. And so going back to the swerve, you'll see that this swerve module takes in just an index 0, 1, 2, 3, and this constants, which has all of the constants built into it. Okay, so now we've configured the swerve modules. And now, for some reason, I guess they have an artificial delay. I don't know why, but whatever. And then this method here is reset modules to absolute. Let's look at what this does. So this loops over each of the modules and it calls reset to absolute. And this is exactly what this offset is used for. Right? Let's say you start the match, your robot turns on and your wheels are here. So the first thing you want to do is tell the robot, go to this offset of 100. And because you've inputted what this front to back means, it knows how to go, boop, okay, now I'm ready to go.
Okay, cool.
Cool?
Yep.
So now this sets up the odometry, or again, the odometry is what,
Is the position on the field, right?
Yes, exactly. So you'll see here it needs some sort of kinematics. Then it says the get yaw and the module positions. So the odometry uses the gyro. Hold on. Okay, so I have 10 more minutes. Okay, so I've set everything up. Okay? Does that make sense so far? Like what we need to set up? Does that logically make sense?
I think so. Everything that's made sense. I think that when I'm actually if I'm actually doing this, I'm gonna need obviously referencing things. But yeah, it's made sense so far.
No, I mean you should reference things. Okay, so then remember the command. The command here called this .drive thing.
Mm-hmm.
So now we're actually getting to how we implement drive. Okay. Again, it has a translation 2D, right, which we spoke about earlier. This represents how fast we want to move with respect to the field or with respect to the robot. This is how much we want to rotate. Are we field relative or robot relative? And is open loop. That's true for now. So this right here, I'm not going to get into this function right here. But actually, maybe we will for a second. So what this function does to swerve module states. Okay, it's a little complicated. There's a ternary condition, which is whatever. So this chassis speed here, wait, hold on. Okay. So swerve module states. It calls this to swerve module states and just ignore all of this, okay? What we get in the end is an array of swerve module states. This basically tells okay. This translation is how fast I want the robot to move, how much I want the robot to translate. This is how much I want the robot to rotate, okay? But now we have to go from the robot's point of view to the individual module's point of view. What does this module need to do in order to get to this ultimate, robot's translation and rotation? Does that make sense?
Yeah.
Right, because at the end of the day, we need to control each of the modules, like how much you have to go, how fast each module has to go, and in what orientation each module has to go. But really, that's kind of an afterthought. What we care about is that the robot moves at this speed in this direction and it's rotating this much. So this to swerve module states converts the robot's point of view to the individual swerve module's point of view. Okay, so that's what this does. And then this calls desaturate wheel speeds. Basically this this to swerve module states might tell a motor to go at more than what it's capable of. So maybe it's actually not physically possible for this motor to rotate that fast. So this desaturate wheel speeds basically takes these swerve module states, which is how fast I want each motor to move, and it like scales it down by the max speed. It just scales it down so that these swerve module states are attainable by the actual motors. And this max speed here is a constant that you can set how fast you want the robot to move at max speed. And you can't set that to 1,000,000 miles per hour because, physics. And then all you do is you call here for each module. I have the corresponding swerve module state. I just tell, hey, front left module, do what I've calculated. And that's it.
Cool.
Right? And then, so that's, and then there's kind of the odometry and stuff like that, which I don't actually know. I don't know where the odometry is called. Hold on. Yeah. Oh, got it. I see. So that's that. So that's what this drive does. And then each subsystem can actually run code on its own every loop cycle. And you do that by by overriding the periodic method that's on this subsystem base. So basically it's a way to tie into the looping cycle. And what this does periodically every 20 milliseconds is it tells the odometry to update its, to read the sensor values from the gyro and update its internal position of the world. Then I guess here what it does is it just puts onto the smart dashboard kind of all of the camcoder, like all of the stats on what each motor is doing, what each module is doing. And so that's how it works. So that's how the swerve drive works. And then the last piece of the puzzle, and I have like, hold on. I have 4 minutes. Then the question is, how does each of the swerve modules work? Right? Because what we did from the swerve drive point of view is we have set desired state, and we've seen the reset module to absolute. So let's see here. How do I reset the motor to the base value that to this 100? So what it does is it gets the camcoder, it gets the degrees, see here, and it subtracts from it the angle offset. So this reads the value of the camcoder, then it subtracts the angle offset which you've specified. Remember how I said it takes this 200, subtracts the 100? That's what it does here. Okay. And then this right here, it also, if there's a gear ratio, then it, takes into account the gear ratio. And then this right here is what actually tells the angle motor to go to this position. Okay?
Okay.
And that's that. So then the other function which we have, which we saw in order to do teleop, is a set desired state. Right? Over here, when we called the drive, we go through, once we have the swerve module states, we say, okay, swerve module, set desired state. So let's look into how this works. So all it does is it calls two independent methods. One is the set angle, and one is the set speed. The set angle basically, okay, so it finds the angle that you want to go to. I don't really know what this is doing, and it's fine for now. Basically, it gets what angle you want to set the individual motor to be, and then you call this method right here. You say angle motor set to this position in degrees. So set to 45. And this is cool because there's a position control, so you can kind of, it actually says this line right here actually makes the module go to whatever you tell it to. Okay, so that's the set angle. Then the set speed is open loop. For teleop, this is always true. So all you do is you take the desired state, so your speed in meters per second, you divide that by the max speed. So this again returns a value from -1 to 1. Because when you call a motor, when you tell a motor to go at 100% of its output, of its capability, you have to send in a 1. If you want to make it go backwards full force, you send it a -1. So this is a percentage. And then you just call mDriveMotor.set, and that's it.
Cool.
From that point of view, it's relatively simple. So what you're going to have to do whenever, even if I'm not here, is you can follow this README here, and they basically tell you, they go step by step through what you need to tune, or what parameters you need to put in. So first you set the pigeon ID, and is it inverted? Again, you can try it true or false, and if it's the other way, then you'll switch it. And then chosen module, you already have that. It's one of the defaults. And then you just fill in all of these. So you're going to take a tape measure and whatever, and you're going to get this value here. Get this value, the circumference of the wheel, drive gear ratio. These should already be set for you because we just bought them. And then you have to set the CAN IDs of the motors. Then setting the offsets. Look, they actually tell you how to align the modules. So use a piece of metal and actually physically align them and do all of this stuff. They tell you how to do it, which is cool. And then also for this, and if you follow these, then when you deploy it, it should work.
Awesome.
Cool. So with that being said, I'm gonna get going.